Welcome. In this lecture I want to give an introduction to electrical submersible pump, also abbreviated ESP. So ESP is an artificial lift method that consists of threading a pump to the tubing and putting that pump as close as possible to the formation to increase the pressure between what's coming in and what's coming out. And I want to make it as close as possible to the formation such that it has best effect. So to discuss how an ESP works, I want to use the diagram that is shown here on the right, and I also want to make a flow equilibrium. So consider we have a vertical well. We have an ESP threaded at the end of the tubing, which is just in front of the formation, in front of the perforations. So I can assume that the suction pressure to the ESP is the flowing bottom hole pressure. And I'm going to plot upstream and downstream the pump, neglecting the presence of the pump. I want to plot the available pressure seen from reservoir to bottom hole pressure and the required pressure seen from the separator all the way to the discharge. And then use that plot to make an analysis. So I'm going to make a plot of pressure with rate. Typically, when we have electrical submersible pumps, we're talking about oil wells that produce oil and liquid and water. And typically it's under saturated reservoirs, although I could also be producing from saturated reservoirs if the gas amount is low. But we're going to make an IPR for this case, like if it's a linear IPR, corresponding to a saturated, undersaturated reservoir. So that's the IPR. That's the curve seen from the reservoir, how much pressure is available at the suction of the ESP, and that is the PWF. And then I'm going to plot also the required pressure curve, which is the pressure that I require to flow against separator pressure for different rates and when flowing exactly at the discharge of the pump. So that curve looks like that. Okay, this is my TPR, and this is for a constant wellhead pressure. So if I assume that I put these two systems together with no pump, then the rate that this well will produce will be this one, Q oil star. And that rate might be too low to be economically feasible, or I simply want to increase the rate to increase revenue and also increase recovery. So usually I want to be to the right. I want to produce a rate which is to the right. Let's say this QO star. So if you see in that condition, I have the energy available from the reservoir is less than the energy that I require to flow through the tubing. So this point here is less than the point here. So the pump is typically used to bridge that difference, to provide that energy, that delta P difference. This is what the ESP has to provide. So that's essentially the function why I use the ESP, is to provide more energy or pressure increase to be able to bridge the difference between these two curves. Of course, the ESP is not only at one point, but actually it might take a few hundred meters. So these curves should be modified. For example, the tubing curve, maybe I should only take, take 200 meters out or 100 meters out of the length, but essentially it's the same result. I just try to make it in a point, concentrate it in a point, just that it will be easier to explain. One thing you can see here from this chart is that when you increase the rate, let's say you want to produce a rate which is much higher than the equilibrium rate, and here we have used the same for both, we should use a different QO star and then this QO ESP, okay, or double star, let's call it double star. Okay, if my QO double star, I want it to be higher and higher, then the delta P that the pump has to provide is also higher and higher. So if we're going to make a plot of that, we want to plot delta P provided by the ESP versus the rate, in this case of oil, if it's an oil well provided by the ESP. We know initially it has to be 0 for a QO star for the equilibrium rate, but then it starts to increase for when I want to produce more and more rate. One more thing also, if we consider depletion, then we know that reservoir pressure, which is essentially this guy here, is going to go down. And now you might have an IPR which looks like that and another IPR that looks like that. You see that at every point in time now the available pressure is becoming less and less, and now the delta P has to be bigger. See, now the delta P is like that, and then the delta P becomes like that for the same rate. Let's say simply we want to maintain the same rate, but then reservoir pressure is declining. So what you see with depletion typically is that if reservoir pressure is going down with time, then typically what I need from the pump, delta P from the pump versus the rate that I'm producing, let's say I'm always producing at a constant rate, is also typically going up. So I have a point for time 1, time 2, time 3. Okay, so it's increasing. Of course, it's not always the case that I want to produce a constant rate. Maybe because of reservoir management, at some point I want to change that rate. But essentially, always have to an increase of pressure. You have a reduction in an increase in delta P if I have a reduction in reservoir pressure. So the pump, the ESP, has operational constraints that we're going to discuss more in detail later, but typically I have a motor. What I install here, has some electrical motor that is providing power for the pump to rotate and to increase the pressure. So that motor typically has a maximum power available to pump. So if I need something more than that, let's say my combination, my delta P is too high and my rate is also too high, probably I won't be able to operate. Also, the pump has an operational map. We will see how it looks like, but essentially it's kind of constraining the combination of delta, P, and QO that I can get, depending on the size and the model. And the suction pressure to the pump, in this case, the flowing bottom hole pressure, typically I want it to be above the bubble point pressure at reservoir temperature or at suction temperature. And that typically is made to try to avoid that gas will be entering to the pump. Liberated gas from the oil will enter into the pump. This is not always the case. Some situations I can produce with pressures below the bubble point pressure. For example, onshore wells, where I produce the gas through the annulus and then I produce the liquid through the tubing. Okay, you see here we have the mixture, oil and gas entering through the ESP. Then I have a gas separator that takes out the gas, sends it through the annulus, and then the liquid goes through the ESP. And in this case, I can produce, this condition is not a constraint anymore, and I can produce at pressures which are below bubble point pressure. However, for offshore, typically we have a packer, a bottom packer, and then all the fluid has to go through the pump. And then in that case, if I have a lot of gas, then if the gas separates, might accumulate in the annulus, and then ultimately it's going to pass through the pump, or it's going to go through the pump. And that's not really very good for performance because the performance of the pump is affected very much by the amount of gas, free gas. So typical gas tolerance in ESP is GBF, is expressed in terms of gas volume fraction equal to 10%. And gas volume fraction, the definition is the Q. This is in local conditions of gas divided by the total Q, which is the liquid and the gas. And the liquid is oil and water. Okay, times 100. So if I have already 10% of the rate of gas at the inlet of the pump, then I might run into trouble because simply the performance is going to decrease dramatically when handling amounts of gas, high amounts of gas. You could see that there are like two ways that we can take these two constraints into consideration. So one might be that I'm doing some design. I know that I want to provide some delta P and some Q, and I want to find out what kind of motor I can install and what kind of pump I can install such that these points fall into the operational envelope. But I could also do it from the operational point of view, that I already have a pump with some motor available, I already have a pump with some operational map, and then I want to make sure that the points that I have are within this fulfill these constraints. So it's like one will be a design problem. I have to select the proper pump for my application, and the other one I have a pump, and then I want to make sure that the rates and the conditions I apply are compatible with the model, with the pump. So the pump, you can read about the ESPs, how it came, how they originated, who started to use them in this article, this link from SPE. But a person which was central in the development of the pumps was Armis Rutunov, which was a Russian immigrant and moved to the US. And he was very kind of straightforward situation, try to put a pump downhole, and then you have to run a motor and try to give electricity to that motor. But there are a lot of challenges related actually with sealing the motor and be sure that it doesn't fail after a short time. So Armis, what he was his main contribution was he could develop a system in which we can send the cable, connect the cable to the motor, and it won't fail under these downhole conditions. So how does it look like? We have the pump. Typically, you have three parts. You have the main pump part where you have the impellers and the diffusers. We're going to discuss about that in a while, but essentially here is where the fluid is coming in through here, and you have that the pressure is increased in all of these usually there are several stages. You might have a gas separator upstream if you are producing gas from the annulus, where you separate and you send the gas through the annulus before all the pump. Then you have at the bottom you have a motor which is providing the power, the torque to rotate all the impellers that you have here. And that motor, actually a shaft goes through it, comes out, and that shaft passes through all the assembly. Okay, and then you have a protector and seal, which is to make sure that none of the hydrocarbon that you are pumping goes down to the motor and enters into the motor, which uses another type of fluid, which doesn't, it will fail if you have hydrocarbon. The motor needs electrical current to operate. So then you're sending that through the tubing hanger. So here you see the tubing hanger. You have a penetrator, you have a cable, and that cable goes all the way down to the motor. So here you see how the tubing hanger looks like. You have a penetrator, a hole, and then you have the cable going down. The cable typically they can be round or they also can be flat. Okay. To avoid when running the pump into the wellbore that the cable will get hooked into different things. So then you typically use these clamps that they open, they clamp the cable, and they keep the cable close to the tubing. Other important components that I haven't shown here, sometimes you have after the gas separator, you have another unit that can help you to either homogenize the gas and to send it through the pump, or also to do further a better separation. And you also above the pump, after downstream the pump, you typically have two components. So first you have the check valve, just after that, which is simply a check valve that avoids that you have backflow. And that typically can be for when the pump stops, that you don't get the backflow and then the motor starts to rotate in the opposite direction, which might damage it. Or also to start up when you want the pump to be primed. You want the pump to have liquid inside and not operate in vacuum. And then you have a bleeder valve, which is a pump, which is a valve which is above the check valve. So you have check valve and then you have the bleeder valve, and that's used in case you want to establish communication between annulus and the tubing. Okay, but I'm not going to go too much in detail, but you can read here. I took these images from this website. So the heart of the pump, what is making the pumping in this diagram, the last part, this pump, consists on a series of stages that all of them are very similar. You might have initially some stages which are a bit different, but all the rest usually are identical. That consists on an impeller and diffuser. So here you have an impeller and here you have a diffuser. The objective of the impeller is to accelerate the fluid, give it kinetic energy. So in this case, the fluid comes through here, and pay attention that this is upside down. So in reality, the fluid will go from bottom up, but now we have it from top down. The fluid enters through this ring. There is a ring here, and then goes through the veins, and then comes out. Okay, so that's where you have this acceleration and the increase of kinetic energy. In this case, the rotor will be rotating on that direction. Okay, and then you have a diffuser, and the diffuser essentially this fluid that is going at a higher speed, that is accelerated, then you are converting now this kinetic energy to potential energy, to pressure. So you are expanding it, diffusing it, and then you are increasing, converting from kinetic energy to potential energy. So the way it is stacked together, and this is the diffuser here, and this is also the diffuser. The way it is stacked together, you see here the diffuser, the fluid goes from here, enters, so it will be 1, enters through here, this will be 2, then comes out through here, this will be 3, okay, which is the same 3 that we have here and the same 2 that we have here. And then after that, it goes through here again, this will be 4. It goes inside the diffuser and then exits through 1. Okay, so then it repeats again. You have a series of, you can put many stages together, so it can be something between maybe 50 all the way to maybe 100 or more than 100 stages stacked up one after the other, and each one of them is going to increase the pressure a little bit, but at the end all of them are going to increase the pressure to what you want it to be. So maybe the flow through the assemblies is easier if we make a cut of the cross section and then we see how it looks like here. So the green part is the impeller and the blue part is the diffuser. So here you see it enter through here, which is the same 2 that we have here. So it will be number 2, flows through the impeller through the vanes and then exits through 3. So 3 is here. Okay, then connects to the diffuser, the inlet of the diffuser, which is 4 here, and then go through the diffuser until it reaches 1 again. So see, this is 1. The diffuser is not rotating, the green part is the only one that is rotating, and then you repeat again depending how many passages you have, how many stages you have. So the way that this impeller rotates, you see that I mentioned earlier that the motor has a shaft that is sticking out and is passing through the whole assembly, and that shaft is rotating. So to make the old impellers rotate, also you use a key mechanism. That is, you make a hole in the shaft. And you make also a hole, I think you can see it from here, you have a small dent in the impeller here and also here. You can see the impeller. And then you put a key in between that is making the two of them that when the axis rotates, when the shaft rotates, the impeller also rotates. So this key mechanism is what is used to be able to fix the gray part, which is the axis, with the impeller. But one thing that this does is only locks them both in place in the angular direction. So if this is rotating, the other one will rotate, but it doesn't lock them in the actual direction. So still the impeller is able to move up and down with respect to the shaft. Okay, and that causes some very particular condition that if, so this is called floating impellers and it's a common configuration of ESP pumps. Some of them don't work like that, but most of them work with floating impellers. And you see that if you have a very high rate through the impeller, the rate actually, the fluid is going to push the impeller up, and then it's going to, you see here, there is some called a washer, that you have a contact between the diffuser and the impeller. And if you have their contact, then you will have friction, and then you will have heat, and then you will have wear, and ultimately it will fail if the rate is too high. Okay, and that's what is called upthrust. Essentially pushing the fluid pushes too much the impeller up, you have too much friction, too much wear, and then it fails. Okay, and the opposite can also occur if you don't have enough fluid, if the rate is low. If the rate is low, then the impeller is going to be laying down on the other part, on the opposite part, on the diffuser. Then you have here a wear of the washer, and then you have also friction, and you have also heat, and ultimately failure. Okay, so this is where upthrust occurs. And this is due to when Q is high, and we're going to see later what do we mean by high, but and this is downthrust when Q is low. Here on the right you have a image that shows, you see the shaft going through the impellers, you see these impellers that are, you have the key mechanism, so they are rotating with the shaft, but they can move up and down. And you have also the diffuser. Diffuser, impeller, and so forth. And then the shaft has to go through all these impellers. Here you see how an assembly, how it looks like, similar to this one. This is a water pump for a water well, but it looks similar for an oil and gas well. So you have the motor at the bottom, you have the cable to the motor, then you have here a mesh which is avoids solids coming into the pump, and then you have all the stages of the pump. And then you have the rest of the tubing. Regarding the electrical system, going more in detail, this is how it looks like. We have the electric distribution system that might come from a power grid or might come from a generator, diesel generator, for example. And then we have a transformer, which changes the voltage to usually 380 volts. Then after that, it goes to a variable speed drive that this is changing, modifying the frequency. The pump have the ability to rotate at different speeds. Typically, it goes from 30 to 70 hertz. So this unit is changing depending on what you need. And this is very important to have flexibility of operation in the ESP. Okay, after that, it goes to this junction box. And then you have goes to the cable and then goes to the same thing that we already have. The junction box first makes a connection with the switchboard with the rest of the system, but also is supposed to be used also for venting in case I have some gases that are going through the sheath of the cable and into, so they won't go all the way to the switchboard, but they can be released before. I also have, beside this is the normal ESP stage, which is, you see that the change in direction, so you have fluid coming through here, then it goes almost 90 degrees to the right, and then it bends again up and then continues. And that very abrupt change of direction is causing that you might have separation of phases. Let's say if you have a little bit of gas, then the liquid will tend to continue straight while the gas can take that bend a bit better. And then you have separation, and this actually causes very bad change of performance of the pump. This other type of impeller that we also saw above, these are more gradual. The change in direction is more gradual. Of course, it takes more space. Now you see it doesn't take maybe 50%, 30% more space. Okay, and then also the delta P that these stages can provide is usually a bit less than this delta P, but they can handle more gas. So by having a geometry like that, you will have less stages. You typically can lift the delta P is less, but then you can handle gas. I think the limit now is maybe 30, 40. Some places they have tried with 60%.